Again, talking about chapter 6. So this is lecture number 26. And we are going to be talking about shearing stress. And there are a couple of things. We've talked about average shearing stress, and we've talked about forces that create shearing stress, which we've called shear. But now, so in other words, we have talked about tau average. Am I good? Boy, that looks really bright and weird, doesn't it? Could I, Christian, I think you're closest. Could you twist these blinds over here? There's a little, yeah, that one and the other one. Ah, thank you. Yeah, we'll get that there. Oh, see, that's so much better. Thanks, guys. All right, so we've talked about tau average, and we've also talked about the shearing force of V. So tau average, we have said, if we have a surface and we are doing something like this, we have an equal and opposite force. Tau average is equal to V over the cross-sectional area. And we also know that V, which we have found using the VM diagrams, we know some geometric relationships, and we also know some mathematical relationships. But the other thing that we've learned is a sign convention for V, which is more or less something that we have just decided upon as a study in engineering science, which way it looks. There's not really that physical meaning like there is with sigma, where sigma pulling is in tension positive and sigma pushing in compression is negative, but V sign convention is just based on direction. And we need to know that because if we add shearing forces or shear, we need to know if we're adding or subtracting them arithmetically. But we've said that this is a positive V if we cut on the right, and this is a positive V if we cut on the left. So we just have an equal and opposite sign convention. So another piece of the puzzle is, if we look at all of the loads that we've discussed, this is the sign convention for positive moment. This is the sign convention for positive sigma. And then, of course, this is, and this are sign convention for positive shear, and ultimately it'll be positive tau. But we always have to keep this. This is kind of a diagram that, like when you're taking a quiz in Mechanics of Materials or Mechanics of Materials 2, you may want to keep this diagram in order to remind yourself of what it looks like. But why do we need to, why is tau different? And I don't know if you recall this, but as a reminder, sigma is approximately equal to sigma average as long as we are away from 20% or so away from the point of application. And that is referred to as Saint-Venant's principle. And it's something that we sort of take for granted, or it's kind of built into our work. So we are saying that here in the immediate vicinity of an applied load, that we're going to have a stress profile that's a little bit exaggerated. So if we don't have like a rigid end cap or something on the end of our structural member, sigma will concentrate in the direct vicinity of the applied load. However, tau average is almost never a good representation of tau. And so the issue is we don't really want to design for tau average. We want to design for what the actual shearing stress is. And ultimately, we want to design for the ultimate, we want to make sure that our object does not, our structural member does not collapse under its own weight, so to speak, because once it breaks, it breaks. So one of the things that we saw when we looked at V and M diagrams, if we have a free body diagram that looks like this, we have a simply supported beam and a W or some sort, let's just even do it more simply. Let's just have a simply supported beam and some sort of a load applied, point load applied to that. Well, what we found is that V tends to look something like this, okay? Whereas M in this case would look more like this, okay? And what this means is that if we look here at that point, the point where the load is applied, the change in V is dramatic and sudden. Whereas the change in load and the change in moment is more smooth, but we have these tremendous discontinuities in V. So tau tends to concentrate, and the tau profile varies radically across a structural member. And another thing you may remember is when we talked about tau being induced from a torque, the tau also went from a minimum of 0 to a maximum of tau max across the cross section. So not only does tau vary radically across the axis of a structural member, it also varies on the cross section. So if you think about what that means geometrically, if we have some sort of a structural member and tau changes across here, so tau 0 is not equal to tau in the middle, is not equal to tau at the end. And we look at a cross section where tau is different here than it is here. This is a two-dimensional part of this is the, if we call this the X component, for example, and then we would call this Z and Y. Tau, X, Y, and Z may be different everywhere. And as engineers, we are interested in tau everywhere, but we're especially interested in the biggest value of tau, because that's what our structure has to be able to support safely. Okay? And so, since tau is inconsistent from point to point, even without changing the load and without changing the structural member, we need to find tau max. And design for it. And when I say design for it, I mean to pick a size and a shape and a material that will bear that particular load. Now, one other thing that tau tends to do, shearing stress, much more than normal stress, tends to concentrate. And we discussed this a little bit back in chapter 1. If you have, for example, one of the ways that we look at an average tau is if we have some sort of a glued splice. And at that point, we can come up with sort of a tau average value. But in general, we don't really have glued splices as much as we have fasteners. And so what kind of fasteners might we have? Well, you might have a welded surface, which is similar to a glued splice. but often you will have some sort of a fastener, like a screw or a bolt or a nail. And if a screw or bolt or nail is, if you have a split here and you have 3 different bolts, all of the Tao on that surface is going to be concentrated on those bolts. That's all you have. So that's why they have to be extra strong. All right? So chapter 6 then, just in closing, is going to talk about the distribution of Tao. And it is Tau at a particular point is a function of V and the size and shape of the structural member. All right, so the discussion can be a little bit complicated, but we're going to break it down very carefully into what those different components mean, so that we can take a cross-section of a structural member being subjected to shear, and say if it's an I-beam, for example, and decide what Tau is here, what Tau is here, what Tau is anywhere on this particular cross-section, and what it is different from this cross-section to this cross-section, and so forth. So, and we're also going to come up with some ideas about where it's going to concentrate, so that we can determine those maximum values. All right, so that's what we're going to do in chapter 6. So for today, no homework, just this short introduction to chapter 6 so that you know where we're going. We take the equations. On Wednesday, I will introduce the equations for shear, and then I'll break down each one of the terms rather than looking at it from a theoretical point of view. And then we'll start to decide how to compute each of those individual components of each individual variables in the equations, and then we'll just develop a strategy for finding Tau and Tau max. All right, so that's it for today, ladies and gentlemen. Have a wonderful day, and we'll see you Wednesday for more fun with math. And if you would please get the, like I said, the homework that's due Wednesday. If you can turn it in on the actual button, that would be best. If not, turn it in late by Friday. So even though we've talked about this before, I'm kind of giving you a deadline where I'll close that envelope, and then everything else will have to come in through the second late submission button.